Good morning. Are there any questions? Okay, so let's move into our next section of material. So next section of material, what we're going to do is to be working with triple integrals. In rectangular coordinates. Okay. So when we're looking at this, okay, so basically we have a couple of formulas that we're going to look at. First is going to be dealing with volume. Okay. So our volume formula, V, is going to be the triple integral over the region, dV. Okay. Our second one is going to be our average value, which we have that the average value is equal to 1 over the volume of the region times the triple integral over the region of some function f dv. Kind of ran out of room there. All right, so what we're going to do now is to take a look at how we are going to evaluate integrals, triple integrals. So taking a look at our first example, we have the integral from 0 to the square root of 2, integral from 0 to 3y, integral from x squared plus 3y squared to 8 minus x squared minus y squared dz, dx, dy. Okay, so if we take a look at this problem, all right, so basically we're going to start from the inside and work our way out. So the first time we're going to integrate in respect to z. So if we do that, we're going to end up with the integral from 0 to square root of 2, integral from 0 to 3y of z evaluated from 8 minus x squared minus y squared to x squared plus 3y squared to 8 minus x squared minus y squared. And then we're going to have dx dy. So if we evaluate this, we're going to have the integral from 0 to the square root of 2, integral from 0 to 3y. So we're going to end up with 8 minus x squared minus y squared minus x squared plus 3y squared dx dy. Okay, so if we clean this up, we have the integral from 0 to the square root of 2, integral from 0 to 3y of, we're going to have 8 minus 2x squared minus 4y squared dx dy. Any questions so far? So now we're going to integrate in respect to x. Okay, so I'm just going to go to a new page and rewrite the last line. So we have the integral from 0 to the square root of 2, integral from 0 to 3y of 8 minus 2x squared minus 4y squared, and dx dy. So if we integrate in respect to x, we're going to have 8x minus 2/3 x cubed minus 4y squared x. And we're going to evaluate this from 0 to 3y dy. Now, the nice thing is that if we plug in 0 for x, it's going to make it everything 0. So it makes it nice. So really, we only have to worry about putting in the 3y. So if we evaluate at 3y, we're going to have the integral from 0 to the square root of 2. And we're going to have 24y minus, this is going to give us 18y cubed minus, we're going to have 12y cubed dy. So if we clean this up a little bit before we integrate again, we're going to have the integral from 0 to square root of 2 times 24y minus 30y cubed dy. So now we're ready to integrate in respect to y. So if we integrate in respect to y, we're going to end up with 12y squared minus, I think we're going to have 15 halves y to the fourth, evaluated from 0 to the square root of 2. At 0, it's going to be 0, which is nice. So all we got to do is plug in the square root of 2. So if we do that, we're going to have 24 minus 15 halves times 4. Okay. So if we do that, we should end up with an answer of what? -6. Any questions? Okay, so let's look at another example. So this time we have the integral from 1 to e, integral from 1 to e, integral from 1 to e, and we have natural log of r times the natural log of s times the natural log of t dt dr ds. Okay, so what we're going to have here is, again, we want to evaluate the triple integral. So we're going to start from t and then work our way to s. Okay, so the first time, if we integrate in respect to t, so we're going to have the integral from 1 to e, integral from 1 to e. Now, these two terms are constants, so we just bring those along. Okay, so what's going to be the antiderivative of the natural log of t? So how we're going to do the antiderivative of the natural log of t?
The integration by parts.
Okay, so if we do integration by parts, we're going to end up with antiderivative is going to be t times the natural log of t minus t. And we're going to evaluate that from 1 to e. And then we're going to integrate with respect to r, and then integrate with respect to s. Okay, so what we're going to have is the integral from 1 to e, integral from 1 to e. All right, so then we're going to have the natural log of r times the natural log of s. So if we plug in e, we're going to have basically, we're going to end up with e minus e, which is 0, minus, then if we plug in 1, we're going to have 0 minus a negative minus 1, or we're going to end up with negative 1. So dr ds. Now, as far as this term is concerned, it's going to be positive 1, okay, but we're going to multiply it out, so we can kind of ignore that. Okay, any questions? So next, we're going to integrate in respect to r. So we're going to have the integral from 1 to e. Natural log of s is a constant. So what's going to be antiderivative of the natural log of r? Yes, it's going to be r natural log of r minus r. And then we're going to evaluate that from 1 to e ds. Well, when we evaluate this from 1 to e, we know it's going to end up with a value of what?
1.
1. Okay. So now, really, all we're going to be looking at is the integral from 1 to e of the natural log of s ds. Well, we know what the antiderivative of this. It's going to be s, natural log of s minus s, and then we're going to evaluate from 1 to e. So we're going to end up with an answer of what?
Just 1.
Okay. And there's your answer. Any questions? Okay. So next, let's take a look at the next example. All right. So our next example, we are given this, and hopefully I corrected this. So it should be the integral from 0 to 1, integral from negative 1 to 0, and it should be the integral from 0 to y squared. And then we're going to do dz, dy, dx. Okay. So what we're going to do first is to draw the region that is being represented here. Okay. Now we know that x and y, x is bounded between 0 and 1, y is bounded between negative 1 and 2. And then z is bounded between 0 and y squared. Okay. So if we take a look at this, okay, so here is our x, here's y, here's z, okay. Now we're told that x is bounded between 0 and 1, so starting off with 0, let's say this is 1. Now y is bounded between negative 1 and 0, okay. So I'm going to go back. So 0's here. Let's say this is negative 1. Okay. So essentially what I'm going to do, and I'm going to redraw this real quick so that I can do a little bit more work over here on the side. slide things over a little bit. So this is x, y, z. We said this was 1. This is -1. So what I'm going to do here is essentially okay. So this is the area that we're going to work with in terms of the xy plane. Okay. Then next we're going to be dealing with this, and z runs from 0 up to y squared. Okay. So if we think about this, basically looking at z equals y squared, we are basically going to be looking at doing the graph of a quadratic. Okay. Now, the maximum value that z can take on is going to be 1. Okay. So we're going to have some points that are going to be up here. Okay. Now, what's going to happen is that our graph, when we draw it, would be coming up to that point, and it's going to kind of do this on both sides. Okay. So what I'm going to do now is complete it. So this is what your graph is going to look like in this particular situation. Now, in this graph, I've got points that are going to occur. Okay, so I'm looking at a total of 1, 2, 3, 4, 5, 6 points. And I need to identify all of those in order to help me to be able to deal with the next bit that I'm going to be dealing with. Okay, so if I start with this point here, what's going to be the coordinate of this point? Okay, so this point is going to be 0, 0, 0. Okay, so now I'm going to deal with this back point here. What will be that coordinate?
And 0, -1, 0.
Right. Okay, so what's going to be the coordinate of this point up here?
Zero, -1, 1.
And then, okay, let's go to this point here. What's going to be the coordinate?
One, -1, 1.
Okay. All right, this point down here.
One, -1, 0.
Yes. And then this point here.
One, 0, 0.
Okay, so we've got all these points labeled, all right? Now, we need all these things to help us what we're getting ready to do next. Because what we're getting ready to do next is to say, okay, we are now going to change the order of how we're going to integrate. Okay, so the first time we're going to integrate in respect to y, then z, then x. So the first time we're going to integrate with respect to y, then z, then x. So we're going to look at it. So we've got our triple integral. We're going to start off with y, then we're going to go to z, then we're going to go to x. Okay, so kind of the easiest thing to do is to start from the outside and work your way in. So we're going to start with x first. So based on our picture, what would be the limits of integration as far as x is concerned? Yes, it's going to be from 0 to 1. So next, we're going to go to z. Okay, so based on the picture, what would be our values for z? Okay, so for now, keep in mind that the last variable is x. Okay, so whatever we are doing, we have to make sure that once we integrate in respect to z, things with x pop out so that we can integrate with x and get a number. Okay, now let's think about this. Does z have any relationship with x?
No.
No. So we don't want any functions on the integral. So we will rather have numerical values. So based on the, the picture, since there's no relationship between z and x, what are the values for z? What are the limits of integration for z? Well, let's think about it. Based on the picture, what's our lowest z value, and then what's our highest z value? Yes, it will be from 0 to 1. Okay. Now, next we have on the inside is y. Okay. Now, if we look at this in terms of dealing with y, so we have to think about it. What is the lowest y value that we have? And in this case, we have to be careful about that. Okay. Our lowest y value, well, no, we don't. What is the lowest y value based on the problem, based on the picture?
0.
Careful.
Oh, sorry, -1.
Yeah, that's -1. Okay, so we're going to start at -1. Okay, now our highest y value actually is going to occur along this curve. Okay, well, this curve is defined as z equals y squared. But keep in mind that what I want to do, once I integrate with respect to y, my next level is z. So I need things written in terms of z. So how can I write this in terms of z? Okay, so y equals the square root of z. But we have to be careful.
Negative.
It should be negative. Because if we're thinking about this, if you think about the parabola, there's actually two sides. And we are dealing with the negative side of this and not the positive side. So it has to be that y is equal to negative square root of z. So that will be the upper limit. Any questions? Okay, so B, we're going to do dx, dy, dz. So on B, we're going to do dx, dy, dz. So we're going to have our triple integral. We're going to start off with dx, then we're going to go to dy, we're going to go to dz. Okay, so we're starting from the end and working our way in. Now z is last, okay? So since it's last, we need it to have numerical values. So what would be the numerical values that we can use for z? So lower to upper.
Zero to one.
0 to 1. Okay, now next level is y. So since the next level is y, that means that when we evaluate, we need things in terms of z, since z is the end. Okay, so that means that for y, we need our limits of integration to be in terms of z. Okay, because we know there's a relationship between y and z. So if we do that, what's your lower limit for y?
-1.
Okay, and then the upper limit would be what? It won't be 0, because you got to remember that what we have to do, we have to follow along the curve. So if we follow along the curve, what are we gonna use? Okay, so it's right there. Okay, so we're going to go to negative square root of z. Okay, now our last thing is x. Now keep in mind that x, nothing, x is just x. There's nothing being defined by x. So x is just going to be numerical values. So what are the values we're going to use for x?
0 to 1.
0 to 1. Okay. Any questions? All right, let's look at C. So C, we are going to do dx, dz, dy. So we're going to have our triple integral. We're going to do dx, dz, dy. Now, since y is on the end, that means it needs to be numerical values. So what are the numerical values that we're going to run y from? Yes, -1 to 0. Excellent. Now, next is z. Now, whatever happens here with z, we've got to make sure that it comes up to be something in terms of y, as far as the limits of integration is concerned. Now, z, what's the lower z value? It's 0. Now, the upper is going to be the curve, which we have defined as what? Y squared. Excellent. Now, x is independent all by itself, so it's just going to be numerical. So what are the values for x? 0 to 1. Good. Any questions? All right, and let's look at the last one. This time we're going to do dz, dx, dy. So we have our triple integral. And we're going to do dz, dx, dy. Okay, so y is on the outside, so it has to be numerical. So what are the numerical values we'll use for y?
-1 to 0.
-1 to 0. X is it's independent of everything. So all it's going to be is numerical values. So it will be what?
0 to 1.
Now z is first, and z is in terms of y. So I've got to be able to pull the y at the end. So what will be the limits of integration for z?
0 to y squared.
And there you go. Any questions?
Wait, so I'm confused, like when it comes to like the terms of like when you do Z, like in terms of Y, like I don't know, like it's not I'm not understanding like
Okay,
why
so when
it's
I'm
the way it
doing
is.
z, okay,
Mm-hmm.
you have to understand that it's based on, I'm starting here, the lower y
Mm-hmm.
value, which is 0. And then what I'm doing is that I'm going along the curve to get the values for z. And the curve is defined as y squared.
Oh, okay.
Okay,
I see. Yes.
any other questions? Okay, so next, what we're going to do is to take a look at how we find the volume. Okay, so our next example, we have this. It says find the volume if the region is in the first octet bounded by the coordinate planes. Okay, so we have it bounded by x plus z equals 1, and we have it bounded by not y equals, but y plus 2z equals 2. Okay, so kind of to help us out with this, what I'm going to do is to graph. Okay, so let's take a look at this. So here's x, here's y, here's z. So I'm going to deal with the first one, and I'm going to do it in terms of blue. So what I'm going to do is just find the intercepts on the x and z axis. So when x is 0, that makes z 1. And then when z is 0, that makes x 1. Okay, so really I have this line right here that is formed. Any questions there? Okay, next, let's deal with this, right? So when y is 0, that makes z 1. So we're going to have this point here. When z is 0, that makes y 2. So 1, 2. And here's a point. Okay, so, oops, we have this line right here formed. Now, we have a base to this region. So let me put the base in. It's kind of sloppy, but so yeah. Here's the base of this region. Okay. And it's not a very good drawing. And then you're going to have one more connector, and that's from here all the way down to this other vertex. So basically what you have is kind of this pyramid shape that we're trying to find the volume of. Okay? Any questions? Okay, so when we do this, when we get it set up the integral, we have to be cautious about how we do this. Okay, now when we set this up, basically what we need to do is we need to pick what variable is going to be at hn. Okay, now if I look at the equations that I have written, both equations have what variable in common? They have z in common. So what I'm going to do is I'm going to put z in the middle. Okay, I'm going to put z in the middle. So I'm going to have my triple integral. I'm going to put z in the middle. Now, I need to decide what I want to go first and what I want to go last. Okay, so if I make that decision, I just need to decide on which is going to be easier. So it's going to be, is it going to be easier for x to be first and y last, or for y to be first and x last? Okay, and it really doesn't matter. Okay, it's just as long as you get the setup correctly. So let's do it this way, where y is first and x is last. Okay? So let's do it with y is first and x is last. Now, if x is going to be last, that means x has to be in numerical values. Okay, so what would be my numerical values for x?
A 0 to 1.
Right. Okay, now the next level is z. Now, that for us to deal with this, you have to remember that the limits of integration in for z have to tie x in. Okay, so based on the picture, what's my lower z value?
0.
Okay, then how is z related to x?
1 minus x.
Okay, and then finally we have y. Now we need to relate y to z. Okay, so let's think about this. Based on the graph, what's the lower y value? It's 0. Now, the upper y value is going to relate y to z, which is going to be what? 2 minus 2z. Okay? Any questions there? Okay, so now what we're going to do is we're going to evaluate this. Okay, so let's take a look at how what that's going to come out to be. So we're going to look at the integral from 0 to 1, integral from 0 to 1 minus x, then the integral from 0 to 2 minus 2z, and we're doing dy, dz, dx. So first time, if we integrate in respect to y, we're going to end up with y. We're going to evaluate it from 0 to 2 minus 2z, dz, dx. Well, we don't have to worry about 0, so if you just plug in the top, so we're going to have integral from 0 to 1, integral from 0 to 1 minus x of 2 minus 2z. And we have dz, dx. So now what we're going to do is to integrate this in respect to z. So we're going to have the integral from 0 to 1 of 2z minus z squared. And then we're going to evaluate that from 0 to 1 minus x, and then dx. Again, luckily, 0 makes it 0, so we don't have to worry about that. But we just have to plug in the 1 minus x. So we're going to have the integral from 0 to 1 of 2 minus 2x minus 1 minus x quantity squared. And then we're going to integrate with respect to x. Okay. Any questions so far? Okay. So let me go to a new page so I can finish this up. So we're going to look at the integral from 0 to 1 of 2 minus 2x minus 1 minus x quantity squared dx. Now I can multiply this out and combine my terms to evaluate this, but I'm just going to leave it in this form and just go ahead and evaluate it in this, integrate in respect to in this form here. So if I do that, I'm going to end up with 2x minus x squared. This is going to be a u sub, so it's going to be equal to plus 1/3 times 1 minus x quantity cubed, evaluated from 0 to 1. Okay, so if I evaluate it at 1, I'm going to have 2 minus 1 plus 0 minus, if I evaluate it at 0, I'm going to have 0 minus 0 plus 1/3. So I'm going to have 1 minus 1/3, or I get 2/3. Any questions? Okay, so let's look at the last example. All right, so the last example, we're going to find the volume if the region is in the first quadrant bounded by the coordinate plane, the coordinate planes, the plane y equals 1 minus x, and the surface z equals the cosine of pi x over 2, and x is bounded between 0 and 1. Okay, so what we're going to do here, again, since we're finding volume, we're going to do our triple integral. Okay, now we got to figure out what order that we want this in. Okay, but based on the functions that we have, both functions are defined in terms of what?
X.
They're defined in terms of x. So since they're defined in terms of x, we probably want the last to be x. We want the last to be x. Okay, and then as far as the next two levels, it's just however you want to. Okay, so I'm going to suggest that we do z first and then y. Okay, now since x is last, it has to be numerical values. Well, we have enough information here to tell us what the values for x are. So what would they be? Yes, it's going to be from 0 to 1. Okay, next is going to be y. Now, considering the fact that these are for the equations y equals. And whatever we have has to tie in x. Okay? So if we do that, what do you think the lower limit for y would be? It would be 0. And the upper limit for y would be what? 1 minus x. Good. Okay. Now for z, z has to tie in x. So what do you think the lower limit for z will be? It will be 0 again. What would be the upper limit? Yes, it will be the cosine of pi x over 2. Okay, so for z, to figure out that the lower limit of zeros, you have to remember that x is bounded between 0 and 1. So if you plug in 0, then you plug in 1. Basically, 0 you get 1. At 1 you get, at 0 you get 1. At 1 you get 0. So we know that the lower value that we're going to get between 0 and 1 is going to be 0 by just plugging in those values. In the same way here, if you plug these values into this, okay, at 0 we get 1, at 1 we get 0. So that's why you are able to see the limits of integration there. Okay? Any questions? All right, so let's evaluate this. So if we evaluate this, we're going to have the integral from 0 to 1, integral from 0 to 1 minus x. We're going to integrate in respect to z. We'll have z. We're going to evaluate it from 0 to the cosine of pi x over 2. We're going to be dy dx. So 0 is 0, so all we got to do is worry about at the top. So we have integral from 0 to 1, integral from 0 to 1 minus x. Then we're going to have the cosine of pi x over 2 and dy dx. Okay, so our next level, we're going to integrate in respect to y. Okay, so we're looking at the integral from 0 to 1, integral from 0 to 1 minus x of the cosine of pi x over 2 dy dz. Well, since we're integrating with respect to y, this is just a constant. So we're going to have the integral from 0 to 1 times y times the cosine of pi x over 2. Put the wrong thing there. Evaluate it from 0 to 1 minus x. At 0, it's 0, so we don't worry about it. So we're just going to put the 1 minus x in, and it should be dx, not dz. Okay, so we're going to have the integral from 0 to 1 of 1 minus x times the cosine of pi x over 2 dx. And we can look at this by just multiplying it out. So the integral from 0 to 1 of the cosine of pi x over 2 minus x cosine of pi x over 2 dx. And the first piece is easy to integrate, but the second piece, how will we handle that? Second piece is not going to be a U sub. Yes, it's going to be parts. Okay, the second piece is going to be parts. So let's look at that. All right, so what are we going to let U be? So,
X.
okay, so X is going to be U, dV is going to be the cosine of pi x over 2. So derivative 1, 0, 1, if we integrate, we're going to get 2 over pi times the sine of pi x over 2, and then we're going to get negative 4 over pi squared times the cosine of pi x over 2. Okay? So if we go through the whole scale of integrating, we're going to end up with this. So for the first term, we're going to have 2 over pi times the sine of pi x over 2, then minus, okay? Then for the second piece, we're going to have 2x over pi times the sine of pi x over 2 minus, the next piece is going to actually be plus, excuse me, 4 over pi squared cosine of pi x over 2. And we're going to evaluate this whole thing from 0 to 1. Okay, so if we plug in 1, we're going to have 2 over pi minus this here is going to produce 2 over pi. This last term is going to be 0, so that's fine. Minus, at 0, we're going to have 0 minus, this is going to be 0. This is going to be a negative 4 over pi squared. So our answer is going to be 4 over pi squared. Okay. Any questions?
Can you go back a slide, please?
Okay. Any other questions? No problem. Okay, so at this time, let's take a 10-minute break, and then what we're going to do is come back and we're going to take a look at doing doing moments and centers of mass in 3D. Um, and it depends on your Calc 2 instructor if they went over centroids in Calc 2 because they're part of the applications of integration. If not, doing it in 3D is not, it actually is a little bit easier than it is doing it in two dimensions. So we're going to take a look at those and show you how that's going to work. So let's do 10-minute break. We'll come back at like 12:06, okay? Okay, for the next section, just for time's sake and everything, what I'm going to do is, which I'm doing right now, I'm going to post the examples, worked out examples for these for you guys to take a look at. Okay, so I've got it posted, and you will see the file um, right after the moment and center of mass notes that I have. You'll see a file underneath that says the examples. And what I'm going to have you guys do is just to go through look at that and go through the examples and everything. They're pretty straightforward and everything, but go through them, look at them, and see if you have any. I'm going to let you guys review those and everything, and see if you have any questions on those. And if you do, then I'll answer those questions on Tuesday. Okay. All right. Are there any questions? Okay. So I'm going to stop here for today. And I really need you guys to make sure that you are caught up with all the work up through all the homework and everything up through the moments and center of mass. Um, we've got basically two more sections before we are done with dealing with triple integrals and everything. And then we're going to move into the last bit of the course, which will be dealing with line integrals and Green's theorem, okay, and dealing with work and flow and flux, okay. So just make sure you, as I said, catch up on homework assignments and everything, and get ready. Also, the other thing is that if you notice there's more notes and there are quizzes left over, that means I'm going to be adding some more quizzes in. So there are going to be more quizzes than I originally estimated for the course and everything, but it actually helps you guys out much more. Okay, so just keep that in mind that that's going to be coming up here soon, as far as the material is concerned and everything. Okay, are there any questions? Yes, you will. Okay. And like I said, they're worked out in detail, each of the problems. Okay. They're my notes and I worked them out in detailed. So if you'll review those and everything, and if you have any questions about those, just let me know and I'll clarify anything that you don't understand. All right, guys. You have a great rest of the day. You have a great weekend, and I'll see you guys on Tuesday. Also, quiz 13 is available, and it will be due on Tuesday. Okay. All right. Take care. Bye bye.
You are currently the only person in this conference.